and welcome to the second online meeting for MTH 129 Discrete Mathematics. So this week, just want to just continue getting us ready for the first assignment. So the first assignment is due end of next week, and it covers all of set theory, logic, and proofs. And so in lectures so far, I've covered everything but the induction part of it, which I want to cover today, just so you guys have got enough time to look at it. Internal students will get things on Monday morning, but you guys, it takes about another day to get access to that. Just want to cover that. But before I do that, just want to cover some logic stuff. So you can see a question here. So this is from the exercises I've got. So this is what I do in tutorials. And it's trying to prove a logic equivalence. So let's just translate the symbols. So this is the little wedge character. Can you just type in, what does that mean? Do you people know what this character means here? Pardon me. That's right. So it's an and. So you've got A and B implies C. So essentially, in terms of logic, that's their two premises and conclusion. So we've got two premises implies C. This is logically equivalent. So that's what triple lines mean. Equivalent to what's this little line here mean? This negative sort of sign. Not, yep, that's right. So not C and, put not C in brackets, not C and B implies not A. So this essentially is, this is a logic equivalent. This is a contrapositive of it. So this is a version of the contrapositive result. We just want to show the logical equivalent. So let's talk about strategies. How do you approach this sort of question in general? Any ideas? What sort of ways do you think you'd try to do it? And we'll then work out how to do it after that. So what sort of methods do you think you have at disposal? If you're not sure, just put a question mark. That's okay. So I mean, you may have done some of these things in ITC 161. Okay, that's fine. So the way to prove two logic statements are equivalent, you've got options. One way is to use truth tables. So if you can draw a truth table up for both the left-hand side and the right-hand side, show the truth tables are the same, that shows the two statements are equivalent. That's one way of doing it, which is what that's the way I approach it. People tend to be more familiar with and, ors, nots, that sort of stuff, and so you probably can just produce truth tables slowly but surely and definitely get there. So that's probably the method that's probably most likely for most people. The other option is to use the rules of the algebra of logic. So there's certain rules in logic about how to simplify ands, ors, nots, and that sort of stuff, and you could use those to simplify it down. So I'll show you that afterwards if you want, but let's just do the truth table approach. Okay, so I'm just gonna just get my, I've got Excel. It's just why Excel, because it does tables really well, essentially. So for a truth table, basically you want to think of all the different possible values for A, B, and C. Now A, B, and C are propositions. They are true, false stuff. So I've got three letters, so A, B, and C, and I want to consider all possible values that I can take. And so they can all be false, and just for short, because it's easy to do with numbers, make them all zeros. You make them, C can either be 0 or 1, and then just consider the various options. So what I would do, so there's 8 options all up, put down a bunch of zeros, put a bunch of 1s down for A. B can either be zeros or 1s. Just copy these sort of things. And then C just alternates between 0 and 1. So this particular way of typing it all down basically gets all 8 possibilities for A, B, and C, and it's in increasing order. So if this is just considered a binary numbers, this is just a binary 0, binary 1, binary 2, binary 3, etc. So just increasing numbers in binary is what I've got here. We'll do more binary later in case you don't know what I mean by that, but that's how you do a truth table. Then what I want to do is I really want to draw a truth table up here for the left-hand side and the right-hand side. I want to do both of them. And so I want to do some expressions, and you probably can't do it all in one go. You probably want to do it in a few different steps. So that's what we're going to head towards. Now, it's, as you can see, if you look around even just what's there, you can see I've got not A and not C, and I might get not B's cropping up, depends how I simplify it down. So I find it useful to have other columns here for the negatives of them all, just so you can read them off really clearly. And so you can, and basically the way to do that is just swap them around. I can do that easily in Excel by just doing 1 minus. So in Excel it does it nice quickly for me, but basically how you do it, if you do it by hand, if any of these numbers are 0, then the negative would be 1. If any of them are 1, make it 0. So just swap the little 1s and 0s around. And 1 means true, 0 means false. And the reason why I put 0s and 1s, as you can see here, is because you can use a bit of arithmetic in Excel to make them really quick for you. That's basically my plan. So I got the A, B, C, we've got the negatives of them all, just so we can do it. So now we've got to look at what our expression here is. So we've got A and B implies C. So there's implication, but I guess I will look at the inside out. So I guess the key part in this thing is there's an A and C here. That's sort of something you narrow down. So I'd work that one out first. So I'll just do A and B, I should say. Let's work at A and B. That would help me with the left-hand side. So A and B, so let's look at our columns. That's A and B. So this one is 0, 0. So if you do false and false, what do you get? Do you guys know? Yep. So you get false, or 0 for short. Let's do another one. Say 0 and 1. So false and true will be also 0. Same thing for 1 and 0. You also get false. And if you get true and true, you get 1. And in Excel, because I want to do it quickly, you can just do it by multiplying the two numbers together, as a matter of fact. So I'm just going to do it quickly, but you could fill them in. And I'm using Excel, you could do them very easily yourself directly. So what I ultimately want to do is the left-hand side is A and B implies C. So let's think about what that means a bit more. So we tend to know and, ors, and nots a bit more clearly. And so there is a truth table for P implies Q. I think for most people, it's going to be easier just to convert this into things you're a bit more familiar with. So P implies Q. So that statement is true if the conclusion is true, or, there's an or here, or if the premise is false. So that's when it's true. So this statement is true so long as either the conclusion is true or the premise is false. Now, what you normally think of using these things is P implies Q. You normally want to consider this, especially if P is true. So if P is true and P implies Q, then we automatically have no Q is true. That's what you use them for. But this is a statement, and we want to talk about if it's being true, the statement's being true or false or not. And it happens precisely when this thing happens. So when we've got A and B implies C, then we can rewrite this in terms of ors and nots as being the conclusion is true or not the premise. So that's the sort of expression we have here. So that's what we want to find. That's really what the left-hand side we want to consider. So it's going to be C or not of A and B. So to that end, I would like to do not A and B, because that particular expression crops up just here as part of it. And the way to do not, again, is to flip the 0s and 1s around. So in Excel, just do 1 minus it. Now, I don't know how well you know Excel, so quite what I'm doing here. I can explain if you want to. It's not required at all for the subject, so you might just happily ignore it, but I can explain what I'm doing if you want to. Just as something extra. But I've got basically worked out not A and B, and the reason for doing that is because that's part of the expression inside. So the last thing I want to do then is do C or that expression. So I really want to do C or, column H, as I've written it here in Excel. And if you think about that, what that translates to being is that A and B implies C. Let's get the letters around the right way. So what we worked out is that A and B, finally get it right. So A and B imply C is equivalent to saying C or not A and B. That's what we're going to work out here. So it's going to do ORs. So essentially, if you want to think about it, you're going, I'm doing the OR of this particular column, so 0, 1, 0, 1, etc., and this column here, the one I've worked out, not A and B. So let's just go through a few. So I'll just color them in temporarily. So here I've got 0, 1. I want to do OR. So this is false or true. What does that correspond to? So if you do false or true, what does that what's the expression follow down to? And it's true. Or 1 as I've written it down, that's right. So it's an inclusive OR. What about 1 or 1? So true or true. What does that simplify down to? Yep, that's also true. And the last one would be sort of one we have is 0, so false or false. What does that correspond to? That's false. And you can do the same thing for the rest of the columns too. So how about I just unhighlight them? So you can do that as being in Excel, just do the maximum of the values. Does it quickly for you. But it gets the same sort of result as we were just talking about. And you can see that in this case, we're getting 1 most of the time. So this statement here, A and B imply C, is true most of the time. The only time when it would be contradicted, so the only time it wouldn't be true, is this case here. So just think about it. The only case when it doesn't work out is if A and B are both true, so the premises are all true, but the conclusion is false. That's the only time it doesn't work. And you go, that will make sense. So if A and B imply C, that means, well, if A and B were true, C would be forced to be true for it to work. So that's the only time that statement's not valid. So we worked at the truth table for the left-hand side, and we want to do the same thing for the right-hand side. Again, just break it down. So you can see, so again, we'll do the same trick as we did before. Do it in red this time, or blue. First of all, I've got something imply something else. I want to convert the implication into an OR statement, just because that's easier. Most people find it easier. I mean, you can do it directly, but I suspect people find that easier. So the way to do that would be, this is logically equivalent to the conclusion, which is not A in this case, or not of the premise. So what we're going to do is we're going to try to find the truth table for this expression. So you can see that if you break it down, the first thing we really need to work out is not C and B. Then we need to work out not of that. And then last, we need to do the OR of that with not A, just to get the whole thing working. So along those lines, we need to do not C and B. Then we need to do not of that. And then lastly, we need to do not A or the last column, so column K in this case. And that particular one would be not C and B implies not A. So that's what we're trying to do. So we've worked out that this expression here corresponds to this an and/or situation. So we just, and then proceed as we would do normally. So this one is an and of not C. So this column here is not C. and B. So I just want to work out the AND of those. And we just do the same things as before. So in Excel, I can do it really quickly. It's B and not C. But it's what we're really doing. If you had to do it all by hand, we're just going through each at a time. So B and not C, that's 0 and 1. So false and true would be automatically false. And you can do the same rest the same sort of fashion. Then you want to do not of that. So just do if it's a 0, come back to 1. If it's a 1, make it a 0. So you can just flip it around. And this lastly, you've got to do the OR. So you want to do the OR of the not A column and this column we just produced. So we're just doing the OR of these two to produce this next one. And I'm just going to get Excel to do it for me quickly. So what we have is this here. That's the truth table. Oh. Where'd it go again? Okay. So what we have here is we now have the truth table for the left-hand side and the truth table for the right-hand side. Now, so long as those two are the same, that would mean that the two expressions are the same, or logically equivalent. You go, they are. Look, they're all the ones in the same place, zeros in the same place. And so the conclusion is, since columns, as I've got it, I and L, or columns 9 and 12, effectively, if you count them, are the same, left-hand side equals right-hand side. So that proves they're logically equivalent. So that's one way of proving two things are logically equivalent. And as I said, you could have done it other ways, but I think that's most direct. So the reason why I mentioned that one is just how you deal with implications in particular. So depending what other subjects you've done, so ITC 161 in particular, you may have seen some of this already. The thing that's probably mostly new to people is this implication symbol. So I want to explain that one. So you can do it using the rules of logic as well, which if you want to, I can show you that. But I'll just move on for the moment unless people want more information there. So if you want to ask a question, now's the time. But I can show you if you wish. So remember, this is for you guys, so ask questions. Okay, how about I just do induction first, and I'll come back to that if there's time. So I'll just do one induction question. So in terms of the assignment, as I was saying earlier, the question 1's about sets. Question 2 is about logic. So it would include questions along that sort of line, vaguely speaking. And the last one's about proofs. I suspect, my guess, I don't know, we'll find out when we do it, is that the proofs question probably will find hardest. Just encouraging you along is that part of proving, so proof is basically writing a bunch of steps, one step leading to a next to reach some sort of conclusion. That's basically the idea. But there's lots of different strategies for it. And with these strategies, so what was I saying? So with these different strategies, part of doing it is if you know the strategy and demonstrate it. So I think I would give you some marks if you can just indicate the strategy. So if you've got a proof by contradiction, starting by assuming that the conclusion is false and the premise is true, and therefore knowing there's something in the middle and you're ending with a contradiction. If you can get the beginning and end, for example, that shows some understanding. May not get you a pass if that's all you can do, but if you can start putting some things in the middle, some of the details in the middle, that can at least get you a pass mark for that sort of question. And maybe even better. And as soon as you start getting the structure around it, then you sort of know where you're going. If you don't really know where you're supposed to be heading up in the end, then you're not going around in circles and you may not get nothing. So knowing the strategy is actually both important to actually help you get the answer in the first place, and therefore I want to give some reward for that. So there's lots of different types of proofs. So one of them is called induction. So this is one I haven't covered in lectures yet. I'll do it in my next lecture. But just to give you guys enough time, I just thought I'd mention it quickly here and do a different example to what I'll do in my other lectures. So induction is a type of direct proof. So direct proof really means you start with a premise and get a conclusion. And it really works by proving things which are connected with counting numbers in some regard. So it's a statement which you can prove for counting numbers. Let's just do an example. I'll show the example first, then I'll talk about the strategy. We have a data structure called a binary tree. If it's nice and balanced, it means that you've got a root node, and every node coming from it has two different branches, so to speak. So that's an example of a balanced binary tree. They're used to sort data, among other things. So they're just a nice compact way of storing information. So a quick way of storing sorted data. The ternary trees are the ones which are most space efficient, but binary trees are still pretty useful. And so they're useful in sorting data. So I guess questions you might ask is, well, how good is it at sorting data? How quickly does it take, etc. So just some questions you might ask is, well, let's take a step back. If you happen to have, as in this case, 1, 2, 3, 4, so you've got 4 rows in this case. So you've got a balanced binary tree with 4 rows. How many elements can you actually squeeze into this tree? What can you get from it? And if you think about it, well, I can see I've got one element, 1 dot in the first row. Second one, I've got 2 dots. Next row, I've got 1, 2, 3, 4. Next one, if you count, it just doubles each time. So you can see there's 8. And so in general, if you had lots and lots of rows, you'd have 2 to the n minus 1 in the nth row after a while. And so the total number of elements in the end would be equal to this expression, just summing them all up. So these sort of sums sort of crop up naturally in many situations. So this is an example of a data structure you might use in computer science. So what I want to do is I want to try to work out the answer for this expression. So one way of doing this is, depending on how much maths you know, you usually might know the answer. This one happens to be called a geometric progression, and so it has a well-known answer. Not all series are well-known though. And so sometimes you go, I'll just muck around, I'll just type in the numbers for the first few, recognize a pattern. So that's what the pattern is. And therefore, and I've recognized a pattern for the first few cases, but I want to try to prove it true all the time, not just for the few cases I've looked at. And one technique for these is to prove by induction. So if you look at it, this is a statement, it's a mathematical statement. I'm going to try to prove it directly. So left-hand side applies right-hand side, essentially. And it really is based on a counting number, n. So this should be true for n equals 0, 1, 2, 3, 4, etc. So it should be true for lots of different values. So that's what induction is really good for. So basically how you do induction is you start with a basic case. So the bottom value of n you want to consider. So in this case, you've got a binary tree. I guess the simplest case you can think of really is the tree is completely empty. So there's n equals 0 rows. That would be the bottom case. So I want to prove it true for that bottom case. That's normally fairly straightforward. In this case, because you've got an empty tree, there's not going to be much playing around. So you start with the base case. Then you have to prove what's called the inductive step. So the inductive step is you assume that the result is true for some arbitrary k value, we'll call it k. So just sum in n equals k in the formula. We assume it's true for that one. Then using that assumption, we're going to prove it true for the next successive number, normally k plus 1. I'll show you what it looks like in practice. So that's the basic idea. So what we're doing essentially then is that the expression for k at n equals k implies expression for k plus 1. Then you can write the conclusion. I'll explain it a bit more now, just how it works. But then you'd write the conclusion and say, well, hence by the induction, the result's true for all counting numbers greater or equal to the starting case. So greater or equal to 0 is what we'll say in this case. So how it works, roughly speaking, is basically we going to prove this result true for 0 by plugging some numbers in pretty quickly. Then using this inductive step, if it's true for p equals 0, that would mean it would be true for the next number along. So it would be true for p equals 1. Using the inductive step a second time, that would imply that it would be true for the next number along, p equals 2. And so on. Well, the inductive step always implies it's true for the next value. So by having a starting point in this inductive step, it would then automatically be true for every single number they're following after it. That's pretty much how induction works. So once you know what the relationship between one step to the next, you can prove it's true for all the time. So it's a really useful technique. And so it's a quite powerful one, really good when you can see a pattern and you can name the pattern, but you want just to justify the pattern always holds rather than just the ones you've just seen. Okay, so that's the theory. Let's see how it works in practice. So I'm just going to take a snapshot. So at the end of the day, we're just going to prove this one. Sorry, they didn't cut out that nicely. So I'm trying to prove 1 plus 2 plus 3 up to 2 to the n minus 1 is equal to 2 to the n minus 1. That's what I'm really going to try to prove. I'll talk about the significance in a second for binary trees. So I'm going to use induction. So let's just write clearly. So everybody knows what we're doing. So just as an aside, most complicated proofs, and we're going to be doing simpler ones in this subject, most complicated proofs use a lot of English words and are not full of symbols all the time. Just to make that clear. So English words are actually a good thing for communicating. But so it's good to say what we're doing. So we're going to use induction. So the first thing is to do the base case. So the base case would be the smallest value you want to consider it for. And as I said, n equals 0, that means no rows at all to the binary tree, is the really simplest case. It's like a pretty default one. So I've really got two sides of the equation. So what's the value of the left-hand side? So what's the value of this left-hand side here when n is 0? Well, basically, it's adding up lots of numbers. The number of numbers you're adding is equal to n. Well, if there's no numbers at all to add up to, it's going to be 0. So I'll push it down since there are no numbers. The right-hand side, we just plug in. So the right-hand side is 2 to the power of n, which is 0 minus 1. Does anyone know what 2 to the power of 0 is equal to? Now, the answer is if you do know, fantastic. If you don't know, pull out your calculator and type in your calculator, essentially is the answer. So your calculator does know. So you need to be able to work it out quickly, at least. So you can plug it away. So someone's having a little go. That's all right. So 2 to the 0, if your calculator can tell you, is equal to 1. And so minus 1. So indeed, anything to the power of 0 is always equal to 1. It's a good thing to remember. But I'm happy to use a calculator. So 1 minus 1 would then give you 0. So you can see the left-hand side equals the right-hand side for this particular case. So basically, the base case is true. Now, in this case, the n equals 0 might be confusing, and it corresponds to the empty tree, which is, people might argue, is not being significant. So you could start this with n equals 1 if you wanted to, and that might make more sense to you. And so the n equals 1, you'd only have just the one term. If you sum n equals 1 in here, you get 1. That might be easier for you to handle, and that's perfectly acceptable too. Next step, but I'm happy to answer the questions when they come up, is do the inductive step. So the inductive step, pretty much, has two bits to it. The first thing is you assume true for n equals k. So we assume that this whole thing is true for some arbitrary integer, k. And that pretty much means I'm just going to write it down again. So I'll write this down and I'll come back to the question that someone's asked. So I'm assuming that this thing here is true and I just write down k's instead of n. So k here is a placeholder for all the different integers that might possibly be. So we start with that assumption and then we do something next. But I'll just go back to the question someone asked is, how do I get 0 here? Really what we're doing here is just summing up n numbers. So if that's the first number, n equals 1, n equals 2, n equals 3, etc. up to n. So there's just n different numbers along here. So if n equals 0, there's nothing to add. There are no numbers at all. So if you're summing up nothing, what do you get? Well, you get nothing. So if you really dislike that case, you could do the base case of n equals 1. In that particular instance, the left-hand side would be just the bottom number, so it would just be 1. That's the only number you're adding up. So just just adding up the first number. That would be a binary tree of just one row. And the right-hand side then would be 2 to the power of 1, n equals 1 minus 1, which is 2 minus 1 equals 1. So you can do that as another base case if you really dislike the n equals 0, 1. And that's okay. I don't think it makes much difference when it comes to binary trees, which were the two results it is. But mathematically it works for either in practical consideration. Yeah, so in terms of this particular instance, so the one I did here, that was an empty tree, so nothing at all. This case here corresponded to a binary tree with just the one node, as you correctly say. Yeah. So anyway, back to what we have here. So you have to prove a base case. So, and it does depend on the context, what the base case is, what the smallest one that's sensible. Next step is the inductive. So you've got to assume it's true for a fixed value. Let's put a little asterisk here. We are going to use this assumption. That's really the critical thing. We're going to use this assumption. So what we're going to do is we're going to then try to prove for n equals k plus 1. So we're going to try to prove it for the next number. Usually the next number is just k plus 1. I guess in the broadest speaking terms, it could be something else, but that's a bit more complicated. We'll tend to stick with the simpler ones in this subject. So we're going to try to prove it for the next one here. And essentially how we're going to do that, we're going to start with left-hand side or right-hand side, whatever's more complicated. In this case, the left-hand side looks more complicated, so I'll start with that. So we're going to start with the left-hand side, which would be 1 plus 2 plus 4 plus etc. Until you get up to k plus 1. So it's going to be one more. So because you've got a series like this one, like they often are, we're going to have one more term on the end here. So you can see I've written exactly the same expression as before, but I've just put one more term, the k plus 1th term on the end. That's our left-hand side. So what I want to do is I want to say afterwards, we're going to say it's equal to the right-hand side. That's what I want to try to say. And if sometimes it's useful just to think what that's going to look like. So the right-hand side normally is 2 to the n minus 1. So if I just plug in n equals k plus 1 into that one. So 2 to the n minus 1. That's what the right-hand side should look like. So that's what I'm aiming for. So it's good to have in your mind, even if you don't write it down, at least what you're aiming towards. That will help you get there. So the basic idea is I've got to go from here, got a bunch of steps in the middle, so one little logic step at a time, and somehow I've got to use the assumption to do it. So when you've got a big series like this one, the series for n equals k just tends to be sitting there already. So it's sitting right there. So the first thing I would do is to just use. I use the assumption. So all this first bit using the assumption can be written as 2 to the k minus 1. Sorry, let's make my writing clear over here. So it's 2 to the k minus 1. And that's using the assumption. And we've still got our plus 2 to the k plus 1 minus 1, which I hope you can, plus 1 minus 1 just cancel out. So I hope you are okay from me saying that's equal to 2 to the k. And what I've really done here is using my assumption. And for short, I'll just say using star, but it doesn't really harm to say using the assumption. So I really have used an assumption. That's the critical part. We're emphasizing that strongly. Now somehow I've got to go from this line here to this line. And you go, well, let's bunch terms together. So I've got 2 to the k at 2 to the k. So I've got 2 to the k. So I've got 2 times by 2 to the k minus 1. So I got the minus 1s lined up. I've got a 2 to the k almost up there. So it depends how much you remember index laws. But 2 times 2 to the k. So when you've got two bases are the same, it's good to write them in terms of powers. It's 2 to the 1 times 2 to the k. And then when you've got two bases multiplying with each other, then you just add the bases together. So adding the bases, that'd be 2 to the 1 plus k. I'm just adding up the bases. And as you can see, if I write it as not 1 plus k, but k plus 1, I get my right-hand side here, just as I was intending it to be. So you don't have to write these bottom two lines first, like I've essentially done, but you at least have in your mind where you're heading towards, so you can try to get there. And again, you can work both directions sometimes. So that's the inductive step. So taking back to the strategy, you do your base case, you do the inductive step, and once you've done those two, pretty much it's done. And so the last thing is just a conclusion. It's good just to make it clear when people are reading it what you've really done. So the conclusion in this case would be, therefore, by induction. So by induction, the result, which you can write down if you want to, the result is true for n greater or equal to the base case. And the base case I used, at least initially, was 0. So it's true for n greater or equal to 0. So that's sort of how you do induction. So just recapping, the strategy is you have a statement that's dependent upon accounting numbers in some regard. You prove it for the smallest value of n that you really want to concern about, usually 0 or 1, but other things are possible. Then you do the inductive step, which requires you to assume the result's true for n equals k. Then, using that assumption, prove it's true for the next one along, k plus 1. Often, as you can see, using left-hand side and right-hand side. And once you've done that, just put a little conclusion at the end just to show you that you understand that it's finished, essentially. And if someone else was reading it, they know that it's finished too. So that's the basic strategy. So there are lots of practice questions, and I'll do another example in my lecture on Monday. So if that's going to be helpful too, so I'll do that in the lectures, and so there'll be more recordings for you. But I won't do this one in lectures, but there might be other ones. So this one's difficult because it's got a lot of powers in it. I've picked it just because it corresponds to an actual physical data structure that you might see. You can do other things with binary trees. I'll explain the question. Sorry. Before I do that, just why we're doing this, the implication of it all. This essentially shows you that the number of data elements m in the tree, if for a balanced one at least, is equal to 2 to the power of number of rows minus 1. So approximately, so roughly speaking, the number of rows is log base 2 of the number of elements, approximately. So that's relationship. So just reversing powers is using logs. And that result's useful. So knowing the relationship between number of elements and the number of rows is handy to know how much space it's going to take and and things like that, and also how efficient it is, which I'll explain in a second. So you can do, so you can use binary trees are good for searching for stuff. So how binary trees are produced in reality is you start with one element, then you add elements one at a time. And every time you add an element, it has to make some number of comparisons. The number of comparisons it makes is how many rows there are in the tree at that point in time, on average. So best case scenario is you just fill it up so it's all balanced. And I want to stress that that's best case. Worst case is much worse than that. And it would fill it up. So every time you fill it, the tree, basically you're filling it just the next row at a time if it's the best case. The number of comparisons is always the number of rows. And so you can show that the number of comparisons you have to do if there's n rows in a tree, in the best case, is given by this sort of expression. I'm just going to wave my hands here at the moment. It justifies at the top if you're concerned about it. You can prove using induction that's equal to this sort of term. So you can use induction for lots more complicated things. So depending on how much maths you've known, you might actually have known how to prove this result directly without induction by using a geometric progression. In this case, this is probably not so well known to people, and so induction is really required for it in this case. Just the implications of it all, just why I mentioned this sort of stuff. If n gets really big, so if you've got a really big tree, then this term, the front term here, gets much bigger than 2, definitely, and also gets much bigger than minus 2 to the power of n plus 1. So this here is approximately equal to n 2dn for big trees. So it's called asymptotic is the fancy word for what I'm doing here, but when n is big, that's approximately what it's going to be equal to. And as I said before, the relationship between the number of rows is approximately equal to log base 2 of the number of elements in it. So if you plug that into here, this is going to be close to saying 2 to the power of n is going to be, that term here is going to be about m, and the n would be approximately equal to log base 2 of m. So at least if you make if you're making a big tree, so you're trying to sort lots of elements out essentially, then the number of comparisons you have to do for a binary tree is in the sort of vicinity of m log m, essentially. And what ends up happening, good sorting algorithms, this is a sorting algorithm, tend to have m log m as the number of comparisons required. So this shows you in the best case, this is a nice, good sorting algorithm. It's worst case, it's pretty bad. It's much worse than that. And so binary tree is useful sometimes, I guess is the conclusion from the matter. But doing so you can see, I'm just trying to show that although induction seems like a very theoretical concept, it is really helpful ways of trying to understand patterns, and confirming a guess for a pattern is actually valid all the time. And what we'll do later on is the way these things often is done via recurrence relationships. So this, you can actually work out the answer for this thing using recurrence relationships as well. And so we will look at that a little bit later on as well. So we'll look at different techniques that you can do for these sort of things. But induction really is a nice helpful step. So I won't try to prove it using induction because I want to do other things, but just trying to show you why we do this, some of the big implications for it all. So just going back to question 1, just so I want to make sure induction was covered. Let's try to prove this result directly. So don't know how good you're right. So what I do is basically I want to use the laws of logic to try to prove this sort of thing. So this is the example formula sheet I've just flicked up quickly. So on the back side of that just has all the rules listed down, and they're written in lots of different places, but this is just a nice convenient reference point. So these are a bunch of different rules that you can apply. Um, and so that's what, and you might know lots of them already. Some of them are, if you understand the symbols, self-evident, hopefully. Um, but it's useful just to have these are useful names for it. So let's just go back. Um, so let's think about what I'm trying to do here. Oops, use black. Cool. So left-hand side is where I'm going to start from. That's A and B implies C. And eventually I want to, at the bottom, I want to say that's equal to the right-hand side. That's when it'll end up. So in my back of my mind, I'm thinking I'm supposed to rearrange this left-hand side to get the right-hand side. That's what I'm trying to do. And so that's where I'm heading. So I've always got that in my mind. So this is where I would think about it. First, I've got A and B imply C. Well, first of all, let's get rid of the implication because I'm often with mucking around with other stuff. So as I said before, that's equivalent to saying not. So then the conclusion's either true or that's an or symbol or not of the premise, which we did before when we did the logic at the truth tables. That's the first thing. Now, what I want to do is I want to try to simplify it. So basically, I want to keep expanding lots. Once I expand, I want to try to factorize, so to speak, to get my other form. That's, I guess, the basic goal. So I've got not of an or. So not of an and, not of an and. So I need to expand that. So the way to expand not of ands or not of ors, etc., is using De Morgan's law. So these bottom two, those two results at the bottom here. So De Morgan's law is really important to expand those sort of things. That's what I'm going to do. So as soon as you say not of an and or not of an or something like that, De Morgan's law is always really useful. So it's C or, and when you've got not of an or, it becomes not of each element, and an or becomes an and becomes an or. So it just swaps the signs around. That's De Morgan's law. So I should give names to what all the rules I'm using here. De Morgan's law is really useful way of understanding things. So it gives you a nice relationship between ands and ors. And so it gets useful in logic a lot of the time. So if you want to try to reverse an and or an or at various points of time, it's a good way of understanding what's actually happening. Next thing I've got or. So when you've got all the operators, so ors are all the same, that means you can just drop the brackets. You do C or not A or not B. So you can just, doesn't really matter the order at all. That's called the associative rule, which makes sense. If the operators are different, so you've got an and an or, so you've got different ones, then you can't just drop the brackets. They're really important, and you have to really expand the brackets, a bit like how you expand, say, 1 plus 2. If you think about 1 plus 2, times by 3, you have to expand the brackets in that case. That's the sort of thing you have to do here, and it's called the distributive law. And that's probably the one that's hardest. I don't know. It's one of the harder ones to remember. When you realize it's exactly the same as this sort of expansion, I think it's a little easier. But because there's so many symbols in the way, that can really get in the way of trying to understand what's happening. But anyway, that doesn't apply here. So yeah, you can see what this basically boils down to is either you've got not A or not B or C. That's pretty simple looking. So now what I want to do is I want to try to group them up together to get it to this sort of form. And maybe a good way of doing it is, I'm not quite sure what I'm going to do, potentially. Maybe start working backwards a little bit just to think where I'm heading towards might be a good way of doing it. Depends how much foresight you have, how much you can do it directly. So this would be my suggestion, would be to work backwards. The right-hand side is an implication, so I convert this into an or. So it's either the conclusion or not of the premise. So that's using the implication. Sorry, that should be that one here and here. Then, in order to try to work backwards, I go, well, I've got a not of a and. So De Morgan's law is going to be useful in that case to expand it going backwards. So I've got all of, so not C. So I didn't want, what does not C correspond to? Any ideas? That's right. So when you've got double negatives, effectively, or a double complement, it just becomes a simple one. So you've got not C, and the and becomes an or, and you've got not B. So I've used not just De Morgan's, plus I've also used the double complement, or double negative. Let's put double negative for short. So I've used both of them to go from this step to this step. And again, I'm going to use the associative law because they're all the same to drop the brackets down. So it's not A or C or not B. So you can say work backwards, and they look fairly similar, which is good. That's what we're hoping for. They're just a different order. Now, when you've got the same operators, just different order, then they're the same. They are the same. And the rule, if you want a name for it, is called the commutative law. So the commutative law pretty much says the order doesn't matter. You can put the order in any way you want it to, which is nice, like you expect. So most of these ones, so these sort of steps here, just adding brackets, removing brackets, and reordering it, are ones you'd hope to be true, and there's just the names next to it just to justify what you're doing if you wanted to. The ones I think are the hardest to remember is De Morgan's law, which I've used in those two lines, and distributive law, which I have not used here, admittedly. So that proves that if you look back, what I've done is I started the left-hand side, done a bunch of steps to get the right-hand side, therefore I've shown that they're the same. So therefore, both sides are logically equivalent. So that's, and hence that proves it directly. So I guess the question you've got to think about is if you had to do that yourself in an assignment, for example, and you could choose whatever way you wanted to, would you prefer to use truth tables or the rules of logic? It's up to you. I mean, I'm not going to force you anyway, and it does depend on circumstance. I mean, in this case, you go, I would much prefer this way, but in a different situation, you much prefer truth tables potentially. So sometimes, as you may have noticed in the assignment, and it's true for your exam, I'll give you the choice. I just say, prove it however you like it. Other times, because I really want to assess one particular way, I might say you have to do it this way. Other times I might give you a choice, but say I really recommend truth tables and whatnot. Up to you. So, and the reason why I do those sort of things is because it's good to make choices. I mean, you need to think what you're more comfortable with. But sometimes I want you to assess some of these rules because sometimes you do need to be able to have some familiarity with the rules, nevertheless. And so I want sometimes to force you to engage with them, which you might not otherwise do. Any questions with that? Now, I know it's 5 to 12, so some people might have to head off in a second. That's fine. I'll just do one last question about proving stuff, and then leave it at that. I suspect it'll take me longer than 5 minutes, but at least I'll talk about strategy first before people have to go. And if you have to go, just go. That's okay. If you've got any other questions before I do this one, fire away. This is a proof question. So you got to prove if something or others, then something else happens. So essentially, this is the form. I've got a premise, which is n m is greater than 100 implies some conclusion. So I've got a proof of an implication. So I'm trying to prove an implication is true. Now, there's lots of different ways of doing these sort of things. So you can prove it directly, or try to, and that is you can assume P is true, then do a bunch of steps to try to get the conclusion. That's the direct approach. That's a little difficult in this point in time because of just how it's phrased. It's actually easier to do it backwards. And the reason is whenever you've got at the conclusion best more simply put down in terms of it's actually easier to work with if you do the opposite of it. It's often easier to do one of the opposite proofs, indirect proofs. So what I'm going to do here is I'm going to try a proof by contradiction. The other approach, you can do a contrapositive, that would also work, which is, again, one of these contrapositive proof by contradiction are sort of ones going backwards. So how I phrase it. So the basic strategy for a proof by contradiction is I'm going to assume the premise. So I'm assuming n is greater than 100. So I'm assuming on the premises. I'm also assuming that the conclusion is false. So I'm assuming essentially not Q. This is the key thing. So assuming on the premises and the conclusion is false. So in practice, what does that mean? So what's the opposite of at least one, n or m is greater than 100, greater than 10. So if at least one is, so that's, if that's false, that would imply that m to n is less than or equal to 10, and m is less than or equal to 10. That would be the opposite of that. I hope that makes sense. If it doesn't, that's really just, it's De Morgan's law, so it's cropping up again. But that's essentially what it is. So, and what I'm doing is I'm aiming for a contradiction. So what I'm hoping to do is, although I've made this second assumption here, I'm hoping to show that this assumption is incorrect, and we should get something absurd at the end. We should quickly get to a situation where that's just not going to be true, and therefore this assumption really is dodgy. We should get rid of it, and therefore the opposite is true, i.e. the real conclusion is true. That's the basic idea. So what I want to try to do is get a contradiction. And if I get a contradiction, what that would imply is, therefore, assumption is false. So hence, at least one of n or m is greater than 10 instead. So if this assumption here is false, then therefore the opposite must be true, which is at least one of n or m is greater than 10. And that's basically the strategy. So what I need to do is just put a bunch of steps in the middle. So I've got at least the basic plan of attack. I'm just going to put the things in the middle. And you go, well, I'm going to try to get a contradiction. So one statement is all about n and a product, n and m. So let's just try to do that. So I'm going to go, well, n times by m then would be less than or equal to, well, n here is less than or equal to 10. So it would be less than or equal to 10. And times m. And m here is less than or equal to 10. So that would be less than or equal to 10 times by 10. So I just show you where I put them. So I've just used these to result. So n times m would be less than or equal to 10m, which would be less than or equal to 10 times 10, which is 100. So next thing is, well, hold on a sec. That already doesn't work, essentially. However, we said that n times n is greater than 100. So one way we're saying that n times n is less than or equal to 100. We already know it's greater than 100. They both can't be true at the same time. So therefore, we get that contradiction we're aiming for, and therefore we've got the conclusion. Therefore, hence we've proved the result. So just taking a step back, how proof by contradiction works is you assume all the premises are true, assume the conclusion is false, do a bunch of steps to then produce a contradiction, so get something that doesn't work, and therefore just put a little conclusion at the end, hence the result's true after all, using the idea of proof by contradiction. So I just wanted to demonstrate some of those sort of things. And again, writing the strategy, knowing where you're trying to end up, I think is helpful to know how you're trying to approach it all. So that's all I wanted to cover today. If you have any questions, fire away first, of course. And if you're watching this recording later on the track, so thanks for coming live for the people who have done it, but I know time doesn't suit anyone, but if you're coming watching it later by recording, then I encourage you to ask questions on the forum, so you can have input into this as well. And you guys are live, you can always ask questions like you've been doing. But thank you for your time. If you have any other questions, you can ask first. That's okay.